So hello and welcome back. This is part 2 of our hardware architecture overview. Just to briefly pick up where we left off, we were talking about CPUs, and with the central processing unit as the main chip in the computers for processing all the logic and computation. It's the general purpose chip, meaning it's the interconnect between all other components in the system, and it's largely solely responsible for the perceived performance of a computer in general day-to-day use. So that is to say, the noticeable part of how well or quickly a computer runs is mostly the CPU, except for edge cases like graphics and storage, which in their own rights have dramatic impacts on the system's overall capabilities, but we'll get into that in a moment too. We talked about the computer cores, which are the small chips within the CPU chip. They are self-contained with their own logic and counting units so that they can process instructions on their own if another core is busy, since computers can only technically do one thing at a time with each wire. So one of the most effective ways to improve the performance of a computer without actually speeding it up and increasing the amount of power or decreasing the physical size of the logic or of the transistors, the gates that the electricity has to run through in order to produce or attenuate a signal. The best way to increase another way of increasing performance was just to add more cores to any single chip so that processes can continue running while another process is still busy doing something else, like say it's waiting for information to come back from the RAM, or it's sending out instructions to another peripheral component. So although their finished operations can be lined up in a queue and ready to be used at the moment the system is ready, having multiple cores means that you can line up multiple finished products, and you could have another core just process those finished products. So it sort of helps you do multitasking in a very parallelized kind of way. Parallelized. So yeah, we talked about clock cycles a bit. That's the actual speed. It's measured in cycles per second, which is the unit of measurement for that is hertz. And typically we talk about gigahertz in these days, but we're sort of getting to the limit of the physical size that these transistor gates can get to, and without switching over to something like photonic or optical computing solutions, we're sort of hitting a brick wall because quantum mechanics steps in and electrons start tunneling through the gates, which makes them harder to contain, which means that we can't store values or reliably check whether or not a switch has been turned on or off. So although there's still some room to shrink things down, and no doubt there'll still be innovations in that regard, there is a limit to the small scale that we can produce these binary circuits through without flipping to an entirely different type of particle to do our processing in. There are about 3 ways of increasing clock speed. One is to reduce the size of transistors, as I mentioned. The second is to increase the power driving the CPU so that the differential between a 0 state and a 1 state is greater. And with a higher power differential, it's not only going to push those through a little bit quicker because of the wire's resistance, not because electrons move faster or slower, technically speaking, but also from the size, there's less distance that they have to travel in order to be signaled from one transistor gate to the other. But the third way of speeding things up is to increase the number of cores and staggering their timings. So if you can't make something faster than, say, 100 meters per second, like if you were talking about a relay race or something like that, one way to move things about a little bit quicker would be to have three runners instead, and staggering them. So by the end goal, if your end was to have 3 batons at the end of the finish line, rather than waiting for 1 baton to reach the finish line before starting another baton, you could have 3 batons running all at the same time. Naturally, they couldn't be received at the other end at the same time, but they could be received boom, 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 one after the other, instead of waiting for the entire race to be run again for the second baton and then again for the third baton. You could have 3 of them ready to go right at the finish line in a staggered sort of offset. So those are generally the 3 ways in how we can speed up processing, and we're going to use all 3 of those in our machine learning algorithms. We're going to be using high clock speeds, well, relatively high. I mean, I come from the 90s, so like processors used to be measured in hundreds of megahertz, so gigahertz to me is exceedingly fast. We used to have single core CPUs, and now there's I'm running on an 8-core 16-thread CPU, so I'll have 16 threads running through, but I'll also have a GPU with a GTX 1650, which is just an entry-level gamer's card, but it's got the Turing architecture of the NVIDIA card that I'm using also has processing cores within it, and those cores are optimized for matrix multiplications, which is ideal for the application that we're going to be using them for. So I've got 896 really primitive, simple cores, but that I can also use. So that's going to dramatically speed up our processing as well. And the CPU is going to be responsible for driving and shepherding those instructions through the GPU and managing the information to be pulled from the RAM and feeding it into the VRAM, the video memory that's located directly on the GPU card, right next to the chip. Generally, GPUs have higher bandwidth RAM too, and I guess that's really important to note if you're doing any of this type of machine learning on GPUs. Having really fast RAM, VRAM on your GPU specifically is going to be even more important than having fast RAM or a fast processor, because that's what's feeding all those cores. So the more cores you have on your GPU and the faster the RAM and the larger the store of RAM you have on your GPU specifically, that's going to dramatically improve performance. But for really large models, you're going to need system RAM anyway, because it's so expensive to make that high speed RAM that there's no real way to avoid using the system RAM for most models. But for smaller architectures, like we're going to be compositing a bunch of smaller models together, hopefully the 4 gigabytes I have of VRAM on my graphics card will suffice for really quick training of all my smaller subsystems. But one other important item worth mentioning is that even if the cores aren't being used, they can still help improve clock speeds by distributing the workload. Because one of the things that processors these days do is they boost their clock speeds when temperatures aren't an issue. So if you're distributing your workload, even if you're only using 4 cores at a time and you have an 8-core CPU, the fact that you can distribute that work across all 8 cores and only use 4 at a time means that your temperatures are going to stay lower, and you can keep your boost clocks active like in perpetuity, rather than being throttled after 20 minutes of running all steam ahead, and then suddenly your temperatures go up and your clock's gotta throttle back to a slower clock speed. So that's one important thing to note too. And this is all done automatically in modern architecture anyway, so you don't really have to think about it, but it's just worth noting that it's not just about brute speed in most cases. So there is no one better answer to what's better, cores or clocks, because it's entirely dependent on the workloads and the expectations of the user and the applications and the algorithms being implemented, etc., etc. So if connectivity with many devices is the main objective, then cores is king. But for intensive data manipulation like video editing on the fly, like streaming video, or scrubbing through if you're doing YouTube videos like these, high clock counts are going to help you scrub through without as much of the jitters. So they've got different benefits and use cases to having either more cores or higher clocks. It's not at all about which one is better for all people. It's more about which one is better for the use cases. So as I said, my current configuration is like 3.6 gigahertz, 8 cores, 16 threads. Pretty mid-tier I've got a X570 motherboard, so it extends my PCI lanes so that I can use expansion cards with NVMe SSDs for when my 32 gigs of RAM is overloaded. Then I've got SSDs up to a terabyte to sort of supplement the RAM. So I've got like stages of fast memory access to run my neural networks off of, and hopefully that should be sufficient to get the prototype running through. But if you play video games and stuff and that's all you do with a computer, you only need like 4 cores. That's plenty, but you'll want higher clock speeds if you're playing games, because that's where you get frame rate and GPU bottlenecks will be from your clock speed, not from your core count in that type of application. So most people rely on clock speeds because most people just play games, or they'll do productivity software that is very very sequential as opposed to parallel. But things like graphics rendering or 3D modeling or CAD design or anything like that, generally you'll want more cores so that you can multitask and you can offload a lot of the heavy workloads onto other cores to keep your CPU core counts lower, which increases your boost clock speeds. Basically, we want to figure out what we want to use for training and running our models if we do decide that we need more processing power than is available to us on our desktops. But in the first part of this, we covered some of the desktop PC architecture, just starting with motherboards and talking about cores, thread counts, and things like that. So I'll go into a little bit more detail in this one just to get a better understanding of how our code's going to be working, because that's the other part of understanding architecture, is not just what to buy to be able to run or operate these types of instructions and libraries and building models, but also for being able to recognize the types of hardware configurations that we can outsource to cloud computes for high performance computing on servers remotely, as opposed to locally on our home machines. And the benefit to this is these machine learning models can be run in parallel. That's going to allow us to scale them quite effectively. Models generally don't scale linearly, so with every little bit of complexity, there's often an exponential value in resource requirements in order to effectively compute that processing. So understanding how it's going to be running through the hardware architecture is going to also help us write code that is more efficient so that we can get more bang for our buck, basically. Because there's not an infinite amount of computing power or money available to rent that computing power, obviously. But even if you could, there's still not enough computing power in the universe to run these brute force. So a big part of our optimization techniques and approaches is going to, and even choosing the type of model that we apply for different applications, is going to depend very heavily on the type of resources that we have available to us to do that. So where we left off with core counts and thread counts, I think was a pretty good spot to leave it at, because that first part, if you've listened through, is going to be very general. So with that alone, you can get started and you can ignore this whole section. But if you do intend to go further and get really deep into the code, like if you're going to be writing in the CUDA programming language to run custom code directly on the GPU, then you definitely want to understand better the hardware behind it, because there's really no point in going that deep into the technology without knowing what the purpose or use case for that would be. In other words, if you're going to be writing code on your GPU, you want to make sure that, first of all, you need to, because it's very labor intensive, as opposed to just plugging values into a library and having it run. But also to know how to structure your code and how to organize the frameworks that we're going to be implementing. Because putting those things together isn't just a mishmash random here and there. It's going to be about grouping things together and compositing them such that we can actually fulfill our objectives. Whereas some of these problems would actually be like physically impossible or intractable entirely without any type of optimization or forethought into the hardware that's going to be running the algorithm. So I guess where we left off with was CPUs, and for this part I'm going to start getting into how the CPUs do that processing. So I'll start with like arithmetic logic units and floating point units, so ALUs and FPUs, which are chips embedded directly into the CPUs, and they essentially form operations and like counting arithmetic, as the name suggests, as well as floating points, which are just decimal points. But these are operations and functions that are not best done in base 2 math, which is how binary math is run. So there's actually a lot of flaws in dealing with floating points in binary systems as we would be using computers. So it's important to know how they work, just because if you're coming across an error, it's very possible that it's just the programming language or the hardware that's throwing the numbers off, if you need that type of precision in your specific model. But we're going to be using activation functions and normalization functions, and I'm going to regularize a bunch of the values, which is standard practice in machine learning. It's not just a thing I'm doing. But when you take a higher dimensional matrix and then you stretch it out into a lower dimensional matrix, like a vector, from a 2-dimensional vector, then there are times when you're going to come into you're still going to come into hardware limitations in those situations, but it's going to be less frequent and it'll matter less because of the smoothing functions that we apply to those matrices when we transform them. But it's just important to know that they're there. So the ALU performs like bitwise and integer operations, and it's critical to all computing and branching statements, and it includes sequencing code and conditional. I said that already. What else is memory management, controller, scheduling, that type of thing. So it organizes and sorts out all the instructions that are going to be sent out towards the other peripherals and devices connected, like the GPU, RAM writing, disk writing, and I don't know, if you're doing audio signal processing, it might go through a DAC or something like that too. So there's all types of different units, but ideally what you want to do is optimize through the hardware first, because that'll be the simplest, most effective, and easiest way to get the most performance out of the hardware that we have available. The reason for that being, you can basically do anything through a CPU because it's multifunctional, multi-purpose, and it can be programmed to do different things. But the issue is when you're using a CPU and software to do all your conversions and transformations, there's a whole bunch of extra circuitry that has to be performed to interpret and reinterpret and compile code, then process the signals and interpret those and send them back, and you know what I mean, read, write, and all that. It's much, much faster if you've got a dedicated piece of hardware, like a chip or something that's built for like noise cancellation or tensor matrix operations or something like that, like tensor cores, or a floating point unit specific for decimal points. You could always do decimal points without a floating point unit, but your CPU would have to do a huge list of instructions just to do all these conversions and spit the number back out. Whereas if you had a dedicated circuit for it, it's basically as fast as flicking a light switch, because that's the thing it does. That's all it's built for, and it can't be reprogrammed. So hardware encoding is optimal in every situation that we can apply it to. And I'm going to be attempting to do this through video encoders when I'm As we said before, when you take in higher dimensional matrices and breaking them down a layer into like a three-dimensional matrix into a two-dimensional matrix, it's similar to rasterizing an image as one example. Another example might be to encode things into a higher dimension. So if you've got a sequence of two-dimensional images, turning those into a three-dimensional scene. And you can imagine that with like photogrammetry, where it's like taking a bunch of pictures around a static object and then having that convert into a 3D model of something else. And given that we're going to be processing a lot of this through Blender, that's the type of stuff that we're going to want to do too. So taking a three-dimensional scene in that respect would be similar to adding another dimension and forming that three-dimensional scene into a time lapse or a video or something like that, where you're going up one level, one dimension by adding a time sequence to it, and then you're bringing it back down one dimension by rasterizing it into a video. And video encoders are great for that, as another example. Doing Fourier transforms to figure out curves and boundary conditions and decision trees and things like that. Those can be done through like audio processing, because maybe you don't know, but MP3s and a lot of compressed audio formats are done like they draw out the waveforms and plot out waveforms based on Fourier transforms, or the fast Fourier transform anyway, which is an optimized version, mathematically optimized, so that'll be a software optimization. But having a hardware encoder for that type of process and a decoder on the other end when you need to read it and then reinterpret it or span it out across another matrix and do another operation with it, applying those signals through hardware encoders is ideal. So thankfully, Blender's got a video engine built into it, and it uses an open source project called FFmpeg, or at least it's not the only one it uses, but it's capable of using that. So I'll be using that a lot too. And the reason for it, again, is because processing these types of transformations through the Blender 3D rendering software, I'm going to use as many of the built-in tools as possible, and I'm going to repurpose as many of the hardware optimized implementations of other people's software within that software to help optimize my models inside of Blender. So that's sort of where we're coming from it. Other than that, the CPU, I guess I should talk a bit about RAM and memory. Random access memory, or RAM, or memory, is not one size fits all for everything. There's system memory, and there's GPU memory, and then there's CPU memory. So RAM just refers to the type of memory. It's a volatile memory. It's information stored in capacitors, so it's much, much faster than reading or writing to a disk. But if it loses power, then it drops all information in it. It's more easily corrupted from signal noise, so interference plays a part in the hardware. And that's probably a bit too much info, but the point is, not all RAM is the same. So typically, the RAM that you'll have on a graphics processing unit, a GPU, which is generally, we're going to be using an external card, but not necessarily. There are many, many processors with built-in IGPs, integrated graphics processors, or APUs, accelerated processing units, or something like that. It's just different for the different branding, but essentially there's built-in graphics processors within many CPUs, central processing units, these days. And I talked about those a bit before, but the important thing to note is that an integrated graphics processing unit is going to be using the system RAM, the system memory, for its video memory, which is much, much slower than a discrete graphics card's dedicated graphics memory, the VRAM, video random access memory. So if you look at any of the marketing materials, see like GDDR5, GDDR6, HBM, high bandwidth memory, that's typically all stuff that'll be on just a dedicated or a discrete graphics card, as opposed to system memory, which the newest out now is DDR5, but it's not very mature yet as a process. So DDR4 is going to be much cheaper and probably just as fast in almost all cases. I would highly recommend, if you're budget conscious or if you plan to do cloud computing once your prototype's up and running or a proof of concept is built, there's really no point in shooting for the highest end RAM speeds, because you're going to get diminishing returns before you even start. It goes the same with CPUs, like we talked about in the first part there. You can get, 6 cores, 12 threads, 8 cores, 16 threads CPUs on desktops now. I mean, it's ideal to have like a Threadripper or something like that with 64 cores and 128 threads, or an EPYC server CPU, but you're going to get diminishing returns before you even start with those too. Because generally speaking, if you can wait 15 minutes for a simple model to train, waiting 17 minutes isn't going to make any difference to your productivity, right? It's not going to slow you down or make your project take months longer. And likewise, if you've got a model that takes 24 hours to render, you're not sitting at your computer the minute it's done rendering. So what's the difference between 24 hours and 30 hours? So for double the price and getting a 20% bump in performance, you might as well just stick with a $300 CPU instead of a $900 CPU. And that goes the same with RAM. The one thing you do get, though, from EPYC or Threadripper, the high-performance workstation CPUs, is you get a bunch more PCIe lanes, and those are pretty much only going to be useful if you're pulling huge streams of data from an SSD. And if your bottleneck in training your model is retrieving data from your SSD or from your RAM, then yeah, maybe spend $3,000 on a workstation CPU. But again, you're not going to be saving yourself months or weeks or anything. It'll be a couple hours here and there. So in the overall scheme of things, like I said, the diminishing returns kick in really fast above the $300 level for CPUs. And that goes the same for RAM. You can get 16 gigabytes of RAM, which will serve you for most any simple model that I'm going to be training. The composite models that I'll be training afterwards are going to be already pre-trained. So training a new model of compositions of other models is only going to be relative to the new model, because the composition is based on pre-trained models, so they're not going to be training at the same time. So you really don't even need more than 16 32 gigabytes of RAM, and that's a DDR4. You can get it at 3000 mega transfers, the overclocked, whatever. You can get that for about $130. So 32 gigabytes would be overkill, but better to have too much than not enough, because having a model half trained that you're sitting around waiting for and then have it crash before it finishes means the entire thing is kind of wasted in most cases for lack of memory. Or worse yet, I mean, it can start thrashing the SSD on your system, like your hard drive, and using your hard drive as RAM. So not only will the training speed drop by 75% and take forever to finish the last little portion of your model, but it's also going to degrade your hardware extremely fast, because these are performing read-writes constantly, and that's the wear you'll get on any of your hard drive. Whether solid state or mechanical, but you definitely don't want to be doing any of this on a mechanical hard drive. So that's my first recommendation. So yeah, the CPU's got its built-in memory, and that's typically anywhere between 2 megabytes and 8 megabytes these days, as of the date of recording this. And that's basically going to be storing a whole bunch of instructions and very small amounts of data, like variables and things like that, things that it's going to be using immediately. And the more times you hit that cache, the more likely it's not going to evacuate it into a lower level of cache. There are usually about 3 or 4 levels of cache, and each one is a little bit, level 1 is the fastest. It's a single layer of capacitors, but it's also the smallest capacity. So sorry if that's confusing. Capacitors just refers to the component that stores the charge and releases it. And capacity I'm referring to is the number of bytes or bits that it can store for any amount of time. So the confusing thing about it is, or I guess it's not so confusing, but you don't really have any control over what's in the cache because the CPU is like built to automatically organize all that for you, right? So if you're writing code and you want to make something as fast as possible and you're iterating through an array, for example, as soon as you're done iterating through it once, if you need any of those items later on in that same function or in that same subroutine, you're best to fetch it right away because you have the highest likelihood that that information's still going to be in the lowest level of cache at that time. So that's just an example of like how to keep into consideration the CPU cache when you're writing code, because it can make a world of difference having something take 3 times longer for absolutely no reason just because you chose to put it on line 100 instead of line 90 or something. So yeah, the CPU cache is mainly though for storing instruction sets, and it's got a few levels. Once it needs that first level of cache for an immediate operation, if it needs to kick something out in the next instruction or the instruction after that because it runs out of room, it'll bump it down to like level 2. And then if it needs it, at least it's still close by and it doesn't have to like go through the motherboard bus and find it in the RAM and then wait for the RAM's timings to fetch it and then do a read write and bring it back. So just worth considering, keeping it in mind. Outside of the CPU, though, you've got your system memory, and that's the thing that's going to store all of like your Windows settings, your application that's open, the text that you've got written but haven't saved to your disk yet, things like that. That type of RAM is much, much faster than your hard drive, but it's much, much slower than the CPU cache, obviously. But the storage volume is orders of magnitudes larger. So instead of megabytes, you're actually talking like several gigabytes typically these days. And that's going to be a huge boon to our work because you can store an entire training set in your RAM and read from your RAM instead of your hard disk. You're going to be able to perform operations on like through your training model or through the training phase of designing your model, or even through implementation. If you can store the whole model in your RAM, it's obviously going to run much, much faster than if it's got to keep stopping, checking with the disk and bringing it back and processing it and so on. And then there's the video RAM, like I mentioned before. So the VRAM that's stuck on the discrete graphics card, if you're using a GPU to do some of your machine learning processing, that's going to be the fastest you can get outside of the CPU. But if you're running, like the GPU is also it's like a CPU where it's got its own cache and its own memory controller, because everything's that's the discrete part of the discrete GPU. It's all integrated onto the same interconnect, the peripheral there. So having that built directly on the card itself just saves you having to run through the motherboard bus to the CPU, have it process it, and run it back into the GPU for it to send it into its parallel cores. Like, it would defeat the purpose if you had to go that whole long route. So on the GPU itself, it's got its own cache so that it can process its own instructions, fetch from its own RAM, and its own RAM is much, much faster than the system RAM, usually, and that's just a factor of cost. So system RAM is much cheaper than GPU RAM, but that's also why GPU RAM usually is in much shorter supply than the system RAM. But it's dedicated just for graphics processing, though, or for machine learning and things like that. So the type of data that it needs to store, I mean, in our cases, we're going to be doing some graphics because I'm going to be encoding a lot of my vectors into texture maps, basically, and then applying texture maps to manifolds of 3D objects, or not necessarily 3D, they could be 2D, but I'm going to be applying those and mapping them through UV channels and rasterizing and processing lighting and reflection and things like that, which is the reason why we're going through Blender. So our VRAM is going to be used heavily just from the render engine itself, so I'm going to try to use only system RAM for the data, and then only when it's processing those operations like dot products, cross products, or divergences, curl, things like that. Only when it's doing that will it grab that the data it needs and the operation it needs, and it'll store that in RAM, which is tiny. But the image that it produces from it and all the vertices that it needs to plot out in 3D space, those are all going to be stored directly on the GPU's RAM. So I want to leave that as much as possible open so that it can do its thing without ever getting overloaded and crashing on us. So that's the GPU, memory, IGP. We've covered cache. I guess we should talk a little bit about hard drives then. Nobody these days should be doing machine learning on mechanical hard drives. You might store a lot of your data like long term on mechanical hard drives, or your models or progress updates, because those can get really big, and it's very cheap for mechanical drives these days to store like upwards of 10, 20 terabytes even, compared to SSDs, solid state drives, which have no moving parts, so they're much faster, they're much more power efficient. But they also degrade faster if you perform too many reads and writes to them constantly. Whereas RAM, you can read and write to it all day long and it'll outlive your computer anyway, just because of the way it's made. There's like a lattice structure of layers of capacitors, so a lower charge will hit the first layer, a slightly higher charge will go through the first layer and into the second layer and pull a bit from it. So that's the difference when you're looking at SSDs, when you hear like TLC and QLC, and basically they're just talking about the number of layers. The more layers you have, the more storage you can get for a cheaper price on the SSD, but it's also going to be slower and it's going to be a little bit less power efficient. So the difference though between is, again, diminishing returns. You're best to just use QLC, and if it dies in 5 years, just buy a new one, because the price is going to drop much faster than the performance benefit you're going to get from paying twice as much for TLC NVMe SSD than paying for QLC. But 1 terabyte of those runs for under $200. They're usually about $150 now, so it's much more affordable, and the performance hit that you'll take for having the extra layer of capacitors or whatever on the chips, the storage units, it's negligible. You couldn't even tell. Even SATA SSDs compared to NVMe's, I mean, you'll boot up a computer in 5 seconds instead of 7 seconds, but like literally nobody can tell the difference that I've met. But if you can, spring for an NVMe, use it to boot your system off of, just so that your operating system and the software that you're using, that all has to be stored somewhere, just to make sure that stuff doesn't bottleneck the rest of your projects. I might consider it for that. But if you plan to do a whole bunch of like video work and 3D modeling work and for rendering, a standard SSD should work fine. Just a 2.5-inch SATA SSD. No need to go hog wild on it. And those are really cheap now. You can get like 500 gigs for like $50. So that's that. Other things that you'll notice when shopping around or looking around is like bus speeds, PCI bandwidth speeds. Again, these are way, it's just hype. It's over-marketed hype. I don't think there's any GPU out right now. Maybe the new 40 series that comes out soon from NVIDIA might use it, but the bandwidth on a PCIe 3.0 is vastly outpaces anything that the card or the CPUs or the RAM could send through the bus to fill it. In other words, if you're buying a high-end motherboard or something because it's advertising PCIe Gen 5, PCIe 5.0, you're never going to saturate that bus, especially not for machine learning, because once you send all the data through it, then it's got to do all the processing, and that's what actually takes time. So doubling or tripling the cost of the card just because of a bus speed that can never actually be used is just absurd. With one of the most common budget GPUs that you can get on the Turing architecture, which is the GTX 1650. It's a low-power GPU. it runs at like 128-bit, and I've never seen it even with graphics rendering and 3D modeling and video encoding and all that. I've never seen the bus hit even more than 50%. I've never actually even seen it hit 35%. So it's impossible to saturate the bus. Maybe on the higher end cards, you might get 50-75% on PCIe 3.0 at 16 X16 slot. But again, like, you're not going to come anywhere near that for machine learning, because all of your processing is going to be done in a batch. You're going to have it all flood into your VRAM. It's going to sit in the VRAM, and it'll be directly on the card, ready to go as soon as the processes are done doing their thing. So it's going to have a queue, basically a waiting list. And if your algorithm takes 3 hours to train, it's going to have, the next hour queued up for sure before it even asks for more information from the bus. And the bus is basically just going to be used for the outputs. So your bottleneck is going to be on the processing, like the instructions, the actual operations being processed, not the data transfer between the CPU and the GPU. So yeah, not much to worry about there. Definitely don't splurge on PCIe 5.0. I probably wouldn't even worry about PCIe 4.0. If you get it, great, you're future-proofed, but nothing is going to saturate the bandwidth of even PCIe 3.0 for the next 3 years at least, unless you're spending more than $2,000 on a graphics card. But in that case, what do you care about $100 extra for a higher PCIe bandwidth? Other considerations with motherboards and GPUs and CPUs, though, with respect to bandwidth, is PCIe bifurcation. One of the best parts of the PCIe lanes is that when you've got an X16 slot meant for the graphics card, you can double up on a second graphics card in another PCIe slot, and it'll bifurcate that 16 lanes into 8 and 8 on the 2 slots. And the reason why that's important in our situation here is just to reinforce and reiterate that because you're never even going to hit the 50% bandwidth limit on PCIe 3.0, if you've got 2 X8 slots at PCIe 3.0, again, you're still never even going to come close to saturating that bus. So even if you're using dual GPUs, unless you're spending $4,000 or $3,000 on just graphics cards, then there's absolutely nothing to worry about even with an older motherboard. But if you absolutely must get the fastest performance for whatever reason, you're best to find an enthusiast channel to give you advice on that, because I can't in good conscience even recommend anybody look for PCIe 4.0, even with bifurcation, but especially not for science, data science. But on that note, there are other peripheral hardware components that would be extremely beneficial and very cost effective if you are looking to supercharge the performance of a budget system or even just a moderate system. If you get an FPGA and figure out and learn how to use it, highly recommend you throw up some videos and show others how to do it too, because the information out there and the tutorials are pretty scarce. But an FPGA is it's a field programmable gate array. Oh, I should have looked that up first. But anyway, it's like a GPU, but it's like hardware programmable. So you get the benefits of ASICs, which are, you build an ASIC specific to one application. That's the only thing it ever does for the rest of its life. It's like that in performance, in the fact that you'll get tons more processes out of it per clock cycle at a much, much lower power draw than you would from a GPU or a CPU, which are more multi-purpose, so they have to have a whole bunch of circuits that aren't being used just in case you wanted to use them for another application. Just sort of the reason we can do machine learning on GPUs is because they're built to do multiple things. but they're not built as multi-purpose as a CPU, which is why a GPU is better at graphics than just a CPU doing it alone. Even though a CPU can technically process graphics, it won't do nearly as good a job because it can't do all the parallelism because it doesn't have the hardwired optimizations. Well, an FPGA is a piece of hardware that you can plug into one of these PCI slots, just like a GPU, and you can plug a bunch of them in if you want, and if you preset them to do tensor operations, and all of our machine learning models are processing tensor operations, then you can effectively get something that's more powerful than even the most expensive GPU at a quarter of the power draw, a quarter of the price, basically. The only difference is there isn't going to be as much support, and there aren't going to be the same level of driver customizations for it, because the only reason driver customizations and optimizations are capable of working on CPUs and GPUs is because they're multi-purpose. So they can read and interpret the logic and code that's written in the driver itself, whereas an FPGA is basically just going to tell it how to address itself, like how to, when I request information, which pinout to send that information to. If I'm drawing too much power or I need more power, I'm going to send it on just super, super basic functionality of turn me on, read and write. The rest of the processing on the FPGA is going to be done from either like jumpers or dip switches, dual inline package switches built right on the FPGA. Some of them will have like an EEPROM, kind of like a BIOS CMOS type of thing, where you have to flash the firmware to set its functionality, basically. And that means like you need a hard reset, you need to wait like 10 minutes for it to wipe itself clean and install new firmware, and there's always the risk of bricking the equipment when you do something like that. But the advantage to doing that is, like I said, you get a mass load of performance, very little power draw, you can run tons of parallel circuits with it, and you can customize it tailored to a specific need, and it'll perform that function so well and so efficiently that it won't be able to do anything else. So that there's limitations, but there's also benefits to it. So if you're looking to supercharge your machine learning training, and you've got a whole bunch of models that you wanna train up at the same time or concurrently, and you don't want to spend a few dollars on cloud processing, then the FPGA is probably the most cost-effective way to go, besides an ASIC. But the cost in an ASIC will be in the production, because it's going to be non-standard. It's going to be physically produced to do that one task or function. And then if anything changes in the framework or architecture of the models going forward, then the entire piece of hardware becomes useless if it's not thought out clearly enough ahead of time. Plus, they've got to be custom built. So these are the types of things that are built for like cryptocurrency mining and stuff. And you'll notice that a bunch of ASIC miners only work on specific cryptocurrencies, and that's because each hashing algorithm of like the cryptographic hashes that run on the blockchain specific to that cryptocurrency is the only thing available to that ASIC. That's the only thing that ASIC can actually process on its own. So a lot of times these miners were running Ethereum, for example, an Ethereum blockchain through a GPU, because the GPU is reprogrammable, and there was a very highly optimized algorithm for hashing through a GPU on Ethereum. And in the background, while it's doing that, the CPU's not doing too much, because all it's doing is waiting for GPU commands or requests or whatever. The CPU can then also manage the ASICs that are running on a separate PCI bus, right? So it's got a couple, 16 PCI lanes on its GPU, 8 PCI lanes on another GPU. Maybe it's got 2 GPUs in the system, both running Ethereum miners. And then it's got maybe a 4x slot and a 1x slot of ASIC miners. And because these ASICs are so low powered and they do all the processing on their own, they don't need, because they can't interpret or read instructions, right? All they do is the thing they do. They don't need instructions. All they need is data. You feed it data and it spits it out. Feed it data, it spits it out. It does nothing else. So you can actually stick in one slot, attach, 8 or 9 or 12 other ASICs to that one slot, and they'll just queue themselves up and just keep spitting data in and out. And then your CPU would be busy all day long processing the data, saturating your motherboard bus in this case. But you're talking about like $10,000 worth of equipment for that type of setup. And designing a PCB and having it manufactured specific to a tailored application, like if you're running TensorFlow or PyTorch or something for machine learning, having one specific to that is kind of senseless and expensive and risky. It would be much cheaper to just use cloud compute through web services or Azure or something like that, rather than having a piece of hardware that an update might break. So if any of those libraries has like a software update or something in the way that they manage, or they change their optimizations in the background, you're either stuck with the old version because the new version won't operate on your ASIC, or it'll be woefully inefficient, which defeats the whole purpose of all the time and energy you put into manufacturing and buying the ASIC. So that basically covers that. So the key points, I guess, just to sum things up, is get as much processing as possible done on this discrete hardware like a GPU, because it's programmable and it's very highly parallelized as compared to a CPU. So you might get like 8 cores and 16 threads in a CPU, and one of them's managing your system and scheduling all of the other cores. So maybe you've got 5 cores and 17 threads or 16 threads, but that's absolute pittance compared to a GPU running 1,000 or 3,000 CUDA cores all doing the same operations in parallel. So a GPU can be essentially hundreds of times, if not thousands of times faster than even the highest multi-core CPU system, because CPU architectures are built to be multi-purpose, and they have an instruction set list of operation codes. I don't know. There's at least 100 of them on x86. ARM has significantly less ARM processors, and RISC-V, no, that's probably getting too much into it. There are other options for CPU architectures, I'll just say that. If you're looking for custom computing, generally if you're going to build your own ASIC or something, you'll do it on like a RISC-V system, because that's an open standard, as opposed to x86, which requires licensing through Intel because they own instructions somehow. They've kept that patent for decades. Even AMD has to pay them for x86. ARM is managed by a company, but they don't restrict anybody's access to using their instruction set. ARM instructions are much shorter. They're much more efficient because of that, and that's why we run our cell phones and laptops and tablets and stuff now off of ARM processors, but that's also what Apple has moved to. They've ditched the Intel x86 architecture or x86 instruction set, and they moved to ARM, and now they're M1 and M2 chips, so the first chips built on ARM, and they are highly power efficient, which allowed them to pump more power into them and make them more powerful by consequence. So the new trend in portable computing, and probably for server computing moving forward, depending on what AMD does in the next few months with their new EPYC processors, they're going to be switching probably over to the ARM license, the ARM model, because most of what we do on computers now, we can benefit like in the high performance segment of things, not generally speaking, but in the high performance segment of things, you want more cores doing simple operations like read writes, because that's all servers really do. Or if they're processing video or something, you can chunk a video into 60 parts instead of just 12 parts, and you can run those concurrently, because a video is sequential, but you have the entire data set, the whole time series, you have access to it right from start to finish before you even start the operation, so you can segment everything. Whereas oftentimes you'll find in machine learning models, you'll have time series data or sequential data, but one step or something might actually be dependent on the output of the prior one, and that type of situation you can't parallelize it. It's just by design it's serialized, so you get no performance benefit from that situation. But in the server space, likely we're going to be seeing a lot more cores, but a lot fewer instructions. But just so you know, and that you're aware, there are other options to even the microcode architecture, the binary instruction sets. And if you did want to design an ASIC or something on your own, you can go to RISC-V, RISC-V, so RISC-V, I guess, and you can look up how to design and set up and install some software to build out your own logic circuits for a RISC-V processor, and then you can have it manufactured and build your own chip, press it on a PCB, and you're off to the races with a highly efficient, small instruction set, dedicated processor specific to your needs. But that would be an entire project in and of itself, and I don't have the funding for that type of project, nor the time, expertise, or experience. So I'll be leaving that aside, unfortunately, for this series of videos. Other than that, I guess I'll link some links in the description just for some of the visualization, the visual aids that I'm using in this video. I've got NVIDIA white paper on their Turing architecture, just for a lot of the language definitions, some specific numbers of, how they use SMs and, what do you call it, like TPCs and GPCs or whatever. Like AMD has their own GPUs too, but they use different terms, and their chips are built differently, so you can't make a like-for-like comparison with CUDA cores and AMD's, what do they call them? I think AMD calls them something different. Anyway, you'll see like 32 processing units on AMD, and you can't say, NVIDIA's got 4600 CUDA cores on their GPU, so it's got to be that much better. Like, they just do different things in a different way. Obviously, if you've got 4600 cores and both your cards are the same size, drawing the same or similar power, obviously one of them doesn't have 1,000 times more of the same units on it. So some of them will be processing, like, dedicated specifically to tensor operations. Other cores will be specifically for ray tracing in these new RTX cards of NVIDIA's. So they might have like 600 ray tracing cores, and those, all they do is trace rays from camera to light source and bounce off of surface normals of 3D meshes. And that's completely separate from a tensor core, which is going to be processing a bunch of like tensor dynamics, like fluid flows or doing curls or forces and physics simulation, basically. And even those are going to be completely separate from like texture rasterization units, which flatten or take flattened images like a UV map and wrap it around like a skin on top of like a jar or something like that, right? It's got to figure out the dimensions and the way that the image is going to be skewed from the perspective, and the depth of field and all that kind of stuff is going to be processed on a completely separate type of core. Not just that it's on a different core, but a different type of core. So these GPUs are basically built in a way that they can parallelize a whole bunch of commonly used applications, and then they make a little, like a grouping of microchips that all have those different abilities, from like floating point units to integer units and all that, and they'll package them into a little square, and then they'll just copy and paste that square, not in software, but like physically, they'll make a wafer with, say, 1,000 of these, and they'll call that a core. Whereas AMD might have a completely different set of microchip bundles, but they could be just as performant or less performant based on the application. So you'll find often with benchmarking that some applications work better with a cheaper GPU from AMD than NVIDIA, and vice versa can also be true. I haven't had the luxury of testing them out and comparing them with machine learning. I chose NVIDIA strictly for the price and for the availability of the CUDA programming language, so I could code directly to it. And at the time I got the GPU, I got it when there weren't drivers available from AMD that worked effectively on Linux. So my reasons weren't entirely anything to do with the best use case for today. It was the best use case for 2 years ago or whenever I got it. And also keeping in mind, I got it for the built-in encoder for doing things like YouTube videos, and it just so happens that I'm also going to be trying to repurpose that video encoder for, if I can and if it makes sense, for optimizing my algorithms today. But that's just because that's what I have, not that that's the only thing that you can use or that it's the best thing to use. It's what I got. So basically what I'm saying, the long and the short of it here is it doesn't really matter what hardware you have. As long as you have something capable of doing concurrent or parallel processing, then you should be fine with most of anything we're doing. Because again, the idea and the concept here is to build out a bunch of small models that just do very specific things, which is the Linux philosophy that works so well. The reason why Linux outperforms Mac OS and Windows systems is because of the modularity of the background. Every piece of it works together, but they don't step on each other's toes. So you've got modules that just do their job. They do one job and nothing else. And if anything breaks, you fix that one module and everything works again. Whereas if you've got a system where all of the different components to it are integrated together, like with Windows, when one thing goes down, then it cascades into failures across the board, and you wind up having performance hits all over your system just because of a small driver issue with your printer or something. And Linux doesn't work like that. Everything's segregated, everything stays in its own lane, and that's what I intend to do with these machine learning models. I intend to build out a bunch of simple small models, an edge detection here, color detection there, next frame prediction there, audio cleanup, so like noise reductions, reflections, and very simple processes that are very, very targeted, and then building out dozens and dozens of these types of models, and then training one controlling model to basically handle which of those small models is giving back the best feedback for a generalized set of situations. So in the case of in the case of building out like text representations, so you'll have like symbolic models for textual representations or descriptions of images that it sees. You could have one big language model like GPT, where you need supercomputers to train it and everything, or you could have a cat model, a dog model, a pencil model, and et cetera, et cetera. And it sounds really tedious, like you'd have to sit there and train each one of these types of things individually, and you'd need data sets with individual labels, yada, yada, yada. But the thing is, with all the number of open source models that already exist, a lot of those things can be cross-referenced and repurposed. So you can use a text-to-image model to also go in reverse and figure out image to text and use that to train other things. So in other words, if you took every word in a dictionary and you had a programmed loop that goes through and trains a model by feeding it training data based on an image generator that produces an image based on every single word one at a time, you could just turn your computer on, walk away, or you could pay a cloud computing service or something like that to run it through a supercomputer far more efficiently, quickly, and effectively than doing it on your home system. But you can automate the process of generating training data that way. and then create a generalizable model based on modular designs of smaller models, as opposed to having one huge, 2 terabyte complex algorithmic function that you have to pass your inputs through every single time you want an output. Instead, we're going to have whatever general input that we throw in, have a controller that basically checks it to all of the pre-trained models and says, which ones of these are giving me coherent feedback? Like, if I put in a word like computer screen or monitor or microphone, and it's spitting back some type of edge detection that has no relevance or bearing, and it's completely stochastic and it has no coherence whatsoever, then my controller model can disregard its output, and eventually it'll just stop asking for an output because it's always incoherent in this type of input feedback, right? Whereas some type of edge detection model for video, if you're looking to see like tracking an object in a video, like a baseball that's flying through the air, or an athlete running across a field, if you're trying to track an object in a video sequence, having even a static image edge detector is going to provide some benefit to that type of feedback that's going to give you a higher score output in your reward functions from the controlling model's perspective. So the output it gets from that type of feedback might be actually similar and useful to a video model, whereas something like an audio noise reduction might also apply to video, in the sense that if the video comes out grainy, or if there's fog that day, or there's like rain or weather, or it's dark, even an audio signal noise reducer might also be able to provide some benefit to that video, but maybe less importance than the edge detection or the boundary separator from the image model, right? So you can combine an audio model with a static image model, and through a video input, this higher order controlling model could use separate outputs of these smaller models to generate a more effective output for the total objective, and get a higher score for its reward cost. And that's sort of how we're going to go about training these. So less is more in our case. So we want more cores, smaller functionality. That's why we don't need higher end hardware. We don't need higher end bandwidth. We don't need faster or bigger memory, because everything we're going to be doing is going to be compositional from smaller models. And our second objective throughout this whole process is going to be running it through Blender, because Blender already has integrated optimizations for all types of different algorithms, from physics simulations to audio and video encoding to building meshes and mapping out UVs and rasterizing images and doing reflection maps and transparencies and smoke and all this other stuff. So the reason why we're throwing this all into Blender, in addition to the visualization capabilities, but mostly is because all the optimizations are already pre-built in. Also because it runs natively with a Python interpreter, and also because it's open source, you're allowed to, or not allowed to, you're just able to, they won't even let you do it with Adobe Suite software. You're able to generate your own code and functionality from within Blender. So for those reasons, it's ideal for this type of project and composition. And hopefully that makes a little bit more sense. And that's why we're going through the hardware so deeply, is because the way we do our code and the way we structure our training algorithms and the way we design and implement our cost functions and reward functions and activation functions and set boundary conditions and all that is all going to be relative to the hardware that we're using, and the hardware that we're using is relative to the design goals and the project's, the research project's objectives, basically. So it all just kind of stems from that. The project's objectives is to modularity over complexity, and reducible complexity is the name of the game. So What else? Yeah, that's it. Right on.